Hi guys and welcome. This is module CM4269, Green and Sustainable Chemistry, and this is the second lecture in the Sustainable Environment unit called Environmental Fate. Okay, this is the menu for today. On the reading, yes, of course, Lancaster Green Chemistry, the course book is useful, but probably more useful for this lecture is I've just chosen Manahan because I actually like the book, but there are a whole range of chemical textbooks called Environmental Chemistry, simply because the Lancaster focus is quite rightly on the processing, whereas this lecture is focused slightly more on the environment. Okay, I think probably we can proceed. Yep, I show this every time and we're actually close to the middle of the module now. And I show this slide every time as well. Now, probably for the first time, we're moving slightly more away from green chemistry, so a lot of the material in this lecture sits more in the environmental chemistry area, and there's even a little bit of biogeochemistry in this lecture. Okay, so environmental fate, it implies that something has gone into the environment, that's something we normally call pollution. So let's spend a moment or two thinking about what we mean by pollution. Of course, if I looked for a definition for anything, surprise, surprise, I'm likely to go for the Oxford English Dictionary, and that particular authority defines pollution as the presence in or introduction into the environment of a substance which has harmful or poisonous effects. Doesn't say to what, poisonous to what, or harmful to what. If we look in the Encyclopedia Britannica, this definition is a little bit more meaty, and I've emphasised certain parts of it. The addition of any substance or any form of energy into the environment at a rate faster than it can be dispersed, diluted, decomposed or recycled, or stored in some harmless form. This definition gets closer to recognising the nature of the environment. It's not just a SAC environment. There are a whole series of processes that go on in the environment, typically physical subsystems, so physically stuff is being moved around. Physical, chemical and biological processes that may dilute, modify, destroy or concentrate the pollutant. And of course, what is emitted may not be the pollutant doing the damage. So pollution is not something that comes out of a pipe and you can go back to where it was emitted 5 years later. It's probably by then gone. It will either have moved, the river will have carried it somewhere else, it would have been speciated differently, maybe it's now in the sediments or maybe it's in the estuaries, it may have reacted either with or without the agency of biology, so it may not be the substance you put in there anymore, and so on and so forth. I'll give you a silly example, one which we'll get to a little later. Okay, so we're happy in principle that the biology or the chemistry may change what goes into the environment, and a silly example of a glyphosate weed killer, and we're going to talk about glyphosate a little later, and really I'm thinking about down here. without going into detail of the formulation, there were two components to this weed killer. One was a very advanced active, which I won't bore you with. The second was a very old-fashioned soap, and it was made by adding 10 molar sodium hydroxide to an ester and forming a mixture like this, very effective against most types of green plants, or leaves at any rate. So the final pH of what was in the bottle was slightly less than 8. When we put this through for regulatory approval, which you have to do for anything you're going to sell in like a garden product in this case, the regulatory authority came back to us and said, right, this has to have an extremely hazardous label, caustic, and I scratched my head and went back to them. And as in many situations, and it's something you should look out for in the future if you end up in this sort of area, the people who were screening the application were not chemists. So they saw 10 molar sodium hydroxide, quite a lot of it. That triggered all of the red warning bells for safety for them. What I had to explain to them is actually there is no sodium hydroxide in the bottle anymore. It's reacted away and you've formed a soap. And when I explained it, it was fine. But the environment is like this. What you put in is not necessarily what you've got. In the same way that what went into the bottle, in this particular example, what went into the manufacturing was not actually in what was in the bottle when it came to be sold. Okay, so what's emitted may not be what is doing the damage, because anything you put in, you can view it as a reactant, which is being acted upon by the chemical, biological and physical processes that are running in the environment all the time. So we're still thinking about definitions. And these are really for completeness. Although pollution can describe entirely natural processes like volcanic eruptions, the greatest air pollution event in all history happened about 4 billion years ago when the atmosphere became oxygenated. There weren't any people around at that time. But in modern times, pollution generally implies that people, humankind, have introduced them into the environment. Continuing on that theme, the human environment is often described as the anthrosphere at the centre of this diagram. And this is a sketch diagram, very neat little idea actually from Manahan, looking at the interaction of the anthrosphere, everything that human beings do, with the atmosphere, the hydrosphere, the biosphere and the geosphere. I won't take you round this in any order, but for our purposes sufficient to realise that this complicated thing that we call our planet, as described by this diagram, contains reservoirs, places where things get stored, and processes, usually interconversion processes, sometimes simply transport processes. And that's the framework, if you like, in which we are introducing our pollution. Okay, another little Manahan diagram. And really about a bit of history and present in one sense. So you have a process, you're emitting stuff up the chimney, you're discharging stuff into the river or burying it into the soil. And this used to be what was done all the time. It was called dilute and disperse. One hopes now that such pollution streams are being reduced, maybe by end of pipe cleanup measures. We'll look at some of those later on in this course, and by remediation measures, and eventually, certainly in terms of green chemistry, we would hope to close these loops, so in fact we don't really emit anything to the environment. So in one sense this is a diagram, although it's not drawn this way, of green chemical processes. First of all, reduction of waste, then elimination of waste, recycling that waste as product for some new process, and economically we would think of that as the reduction of externalities. Because remember, all pollution is actually an externality, an economic externality. Okay, we have three major compartments in the system we're looking at. We have the atmosphere, we have waters, and we have terrestrial. I'm going to include the biosphere in that, although we're not going to think too much about the biosphere in this lecture. Well, actually we are, but as you'll see, biology is everything and in everything, but we won't formally think about it as a subsystem. Right, let's focus in a little bit. Quite a lot of what we're going to be thinking about in this lecture is water, and therefore it's probably worth taking a little trip through the environment and thinking particularly about water. Okay, so we have our factory, our car or whatever. Some of its waste goes into the atmosphere, where it joins in the normal hydrological cycle, atmospheric chemical cycle. Some of it will come down as rain. It may be stored as come as snow, be stored as ice, but eventually it will come through the soil. It will probably join surface water. If it joins surface water, it's likely to also then become part of the soil water reservoir, and by percolation end up in groundwater. All fresh waters eventually get to the oceans, either the deep ocean or the shallower ocean. All ice eventually melts. Any pollutants in the rain that comes down will be taken up by plants, and some of those will be re-emitted to the atmosphere, and so on and so forth. It's a complicated system, and bear in mind what I said earlier. The fact that you emit pollution in one place doesn't mean it will still be there waiting for you. These are the types of environmental processes that move things around. We're not going to talk about the chemistry that goes on in some of these, not very much anyway, but nonetheless all of these act to move stuff around. The numbers on here are thousands of cubic kilometres for storage and thousands of cubic kilometres per annum for the exchanges, the black arrows. So in terms of our interest, our main reservoirs in the atmosphere, we have reservoirs of water, clouds, and in the gas phase water vapour, and ice, freshwater sediments, marine waters, marine sediments as well, life, soil waters and groundwaters. I'm not going to be too interested in this lecture on anything in italics. So we're not going to think about atmosphere and ice. We're not going to think too much about marine sediments or too much about life. But we're going to focus on surface freshwaters, surface water sediments, surface marine waters, soil waters and groundwaters. Okay. And this is just a reminder, you've seen this diagram before, I think. This is a more biogeochemical diagram of the hydrological cycle you were just looking at. And again, we're going to look a little bit about box models in this lecture. You can think of this in exactly the same way as you do a mass balance for a chemical process. And anyway, we'll move on. So, in terms of what we're dealing with, we have the sensible transport of matter, the pollutant in this case, either as a gas, solid or a dissolved solid. The kinetics of the carrier systems, or the chemistry of the carrier systems of a transformation, the thermodynamics and kinetics of the pollutants will determine where the pollutants eventually end up, in what chemical form they are, and what their lifetime in any given reservoir is. Okay, something which is important, although not vital to this lecture. This is a little table of the 4 planetary systems: biota, atmosphere, oceans, lithosphere, and this is their approximate mass. Tor is the residence time in those reservoirs. If you like, it tells you about turnover time, how much activity there is actually in the reservoir. And I think you can see here that the larger the reservoir, the slower the time scale. So lithosphere is the largest, geological processes occurring on the millions of year time scale. The oceans, smaller, processes up to maybe 800, 1200 years. That's typically the residence time of the deep water circulation of the planet. The atmosphere, things happening, again a much smaller reservoir, again things happening on the time scale of days and weeks. And finally the biota, the tiniest of the reservoirs but the most active, things happening on the minutes and seconds time scale. So the mass of a reservoir is proportional to the time scale of the activities occurring within it. That's just general knowledge. We won't come back to that particularly, but it's a good thing to remember. Okay, so now this is a little box model, and I want you to think about the mass balances that you did for chemical plants, because you're going to be doing them again, except this time it's not going to be in a chemical plant, it's going to be in the environment. So let's have an example. This is a place called Loch Fleet in Scotland. I nearly drowned on this loch, actually. And I'll show you a picture in a minute. What is the water level, or the amount of water in that loch, going to be controlled by? Well, first of all, the sources of water going into that loch, and then evaporation from the loch, maybe streams leaving the loch, and maybe infiltration from the loch into groundwater. So using this type of logic is called using actually box models and mass balance. The flux of any particular flow of material delineated by the arrows is equal to the amount. If we're looking at maybe this flux, we're looking at the amount of material in the reservoir, in this case Loch Fleet. A is an amount, it's concentration times volume. If we're thinking just of the amount of water maybe, then that's fine. So the flux is, evaporation is the amount in the reservoir divided by the residence time in the reservoir with respect to, in this case, evaporation. I've defined the terms here. It's very, very similar to what you were doing in the mass balance stuff. But of course, now we're looking at the natural environment rather than anything else. And for completeness, this is Lockfleet in southwest Scotland, in Galloway, a very beautiful part of the world. I recommend it. There aren't any in this picture, but look out for the belty cows. They're very friendly beasts. Anyway, okay, back to the lecture. Okay, so that's Lockfleet, and the golden rule, as in your mass balances, is that the flux into any reservoir equals the flux out of that reservoir. So now, using the tool here and the tool here, you should be reasonably comfortable in developing mass budgets of processes in the natural environment. This is just a carbon box model giving you a broad idea of the fluxes of carbon moving around between the ocean, the atmosphere, vegetation, soils, that's the biota, and fossil fuel combustion, and the amounts of carbon in those reservoirs. All of this is purely using these two tools. Anyway, okay. So, what is a reservoir? Well, yes, the atmosphere is a reservoir, the oceans are a reservoir, soils are a reservoir, groundwater is a reservoir. They're the big picture, if you like. But they are reservoirs for different things. So, if I were to tell you that horses' kidney stems are reservoirs for lead and mercury, it turns out that, well, actually, our own kidney stems as well. Kidney stems are mostly made of cystine, which contains lots of sulfur. And so when mammals take in heavy metals like lead, cadmium, they need these like a hole in the head. They tend to be mopped up by our kidney stems. The question as to whether it's storage or anything more than that is not at least I'm not up to date with that debate, but I don't believe it's understood. I think it's thought generally to be storage. And equally, marine and freshwater and land mollusks store certain things in their bodies. Birds, and we go round the whole list of things. Anywhere with an appropriate sink chemistry, be it a horse's kidney stem or be it an estuarine sediment, will be a sink and therefore a reservoir. What ends up where is determined by the pollutant stability, solubility and volatility. Okay, I've probably just said that, so that's fine. If we're thinking about soils, it's important to know what type of soil you're dealing with, the structure, because some soils are very well drained and therefore the main path out of them is in water. Others are very got a lot of clay in them, clay soils. At Singapore actually soils are like this, and therefore a lot of the pollutants maybe stay in the soil because of the structure and type of soil. Groundwater, local hydrological conditions, depends on how fast it's moving. Let me give you an example. The hot springs of Bath, the water starts in the nearby hills. It takes about 20,000 years for that water to fall, after it's fallen on the ground, to get into the groundwater and then travel in the groundwater till it comes up in the springs. Clearly that's a very different situation from water that falls in a river and just flows down the river. And through all of these, biology, it's the great chemist. Often chemical reactions are mediated by the biology, certainly in water, sediments and soils. It's the fungi, well, it can be all sorts of things, the bacteria, the algae, whatever, the plants. I'm not going to talk particularly about them, as this isn't a biology module, and I'm not competent to talk about it anyway. But nonetheless, understand that the chemist in the environment is often the biology, not in the atmosphere, but probably most other places. Okay, so movement of substances through soils and waters. These are the types of things that we're interested in. Persistence, bioavailability. The more bioavailable something is, the more likely it's to be broken down or moved. The chemistry, the reactivity of both the environment and the pollutant. The chemical properties, typically the solubility, the boiling point or the volatility. The partition coefficient between octanol and water, which is used, it's called KOW, it's used extensively in the environment as a way of assessing the way that a pollutant will move between soil and water. Partition coefficient between organic carbon. Most pollutants, especially organic ones, have an affinity for the organic carbon, and therefore it's important. And KD, the general partition coefficient, and KH, the Henry's law constant. So, soil complexation, ion capacity. These typically are the types of property which determine what your pollutant's going to do and where it's going to end up. So for a moment we'll take one of those, the Henry's law constant, you remember from your first year. It's the partitioning between the liquid and the gas phase. And you need to check for the units, but these are in the concentration in the aqueous phase divided by the pressure in the atmosphere. So moles per litre per atmosphere. I'd like to look at the range of these Henry's law constants. These are as one gets, the constant gets smaller, so the substance is less soluble. Now, to give you a reference, methane sulfonic acid is a natural product, oxidation product of dimethyl sulfide in the atmosphere. It has a Henry's law constant of 1 times 10 to the plus 12 moles per litre per atmosphere. So if you are producing pollutants and you know their Henry's law constants, it will help you to know quite easily whether they're likely to come down in rainfall or not. Anyway, we'll talk more about this sort of stuff in a minute. Okay, so I'm not going to go through the next slide in any great detail. Everything eventually is linked, mostly according to chemistry, with everything else. So most things get most places according to their chemistry. So here we have a little sketch diagram of atmospheric emissions, sulfur dioxide, maybe from a power station, NO2 maybe from land transport, ammonia possibly from livestock. Some of those are oxidized and end up in clouds and therefore in rain. Some of them are dry deposited onto the ground. For your reference, if something comes down in rain, it's normally called wet deposition, and the residence time in the atmosphere with respect to wet deposition is about 4 days. Dry deposition is a gas phase process where gases deposit directly onto maybe crops or vegetation. Usually it's one of those two. Typically that has a residence time of about 2 days. So ozone or sulfur dioxide as pollutants. Much of those pollutants dry deposit onto crops and in point of fact damage those crops. Okay, this is just a little sketch, and I want to draw your attention to the groundwater aspects of the environment, as I suspect many of you might not have met this area. So you have streams here, and we have a tree, we have some houses. Water from these streams is all the time infiltrating down and joining the groundwater. So this blue line here is the, if you like, the level of the groundwater underneath the ground. So if you were to dig down maybe here, you'd have to dig this deep before you could meet the groundwater and dig and have a well. Notice where streams are, because they're putting water in, the groundwater level rises, and at the stream the ground level is actually the same as the water level in the aquifer. This whole area here, flooded area, is called an aquifer. The brown stuff here is basement rock, and water flows downhill in the aquifer exactly the same way as on the surface of the ground. So here it's flowing down gradient and eventually will discharge into the sea. Note in this area, which is still got water, but it's not the sort of completely inundated area, this area has, up here, has both air voids and water in contact with the soil, whereas down here there are no air voids, it's saturated with water. And obviously you've got your groundwater flow. I should mention, not relevant to this module, but where you have a land-sea interface, for part of this aquifer there will be a seawater intrusion, so part of the aquifer will be saline or salt. Now, if there's a strong flow this way, which generally means that people aren't taking water out, so for instance if there were wells here, that would reduce the level of the aquifer and reduce the flow. This tree is pulling water out, which is why the aquifer surface dips by these tree roots. If you reduce the flow of an aquifer, then the pressure from the seawater will mean that some of this will be salt. Anyway, not really relevant to our module, so we'll continue, but good general knowledge. And again, simply underlining the last slide. Wherever you have surface water, that is where the groundwater or the aquifer water table is. And I'll leave that with you. So you have streams, you have a well there, and again, you've got depression of the water table. The point is, anything that is in the soil will probably get into the surface water. If it gets into the surface water, it will probably end up in the aquifer, that is in the groundwater. So pollution doesn't recognise any boundaries. The only thing which determines where it goes to is the chemistry and the physical systems. So basically any pollutant that ends up in the soil will end up in a river, in the groundwater, and in the river, potentially in the sea. Just another little diagram of the soil structure. I'm not going to talk about this. This is basically mass balance again. You might recognise change in mass of pollutant with change in mass of reactant in a chemical process. Exactly the same ideas, and just apply to the environment. Okay, time to stop, I think, talking about those processes, and let's see how this actually translates in terms of movement of substances through the environment. So we have our farmer or our person putting a pesticide on some weeds maybe. The problem is the pesticide doesn't just end up on the weeds. Yep, some of it does, and it will kill his weeds, that's great. Some of it, however, will wash into the soil. There, it gets absorbed into the soil maybe, or possibly it's bioavailable to other organisms. The soil is you can think of the soil as one large collection of organisms, from fungi through to insects through to mammals. A lot of biological processes, so a lot of things become bioavailable in soils. Some of it may be leached into the groundwater. So his pesticide, which was for his weeds, some of it's gone into the groundwater. Some of it may be volatile. So either directly from there or via the soil will be volatilized into the air. If it's bioavailable, trees are likely to take it up, and then the pesticide is within the tree. And falling leaves have pesticide in them, and again goes into the soil. So I hope what this diagram demonstrates is that boundaries are in our heads. It's the chemistry of the molecules that you are emitting, the so-called pollutant, which determines where it ends up. I'm not going to read this. I will recommend this reference to you, really showing you that there are a number of factors that determine how persistent a pesticide is, either in the soil or in a plant. And yeah, recommend you read that. I'll also try and put it onto IVLE for you. We'll stray for a moment into the concept of bioavailability, really so you have met it, nothing much more. If you're studying bioavailability, you're usually talking about an area of science called ecotoxicology. And it's about how stuff travels through the biosphere of the environment and how the biosphere interacts with those substances. Where does it accrue? Is that accrual of pollutants good or bad? So for instance, if we look at modern processes, we know that birds and mosquitoes carry various pollutants in them. What if that pollutant were actually an immunization against malaria or dengue fever? There is current research really trying to establish whether if we introduce low levels of certain materials into reservoirs, for instance, or places where mosquitoes breed, we're not going to have to worry too much about malaria or dengue afterwards, because the mosquitoes themselves will be immunized. And phenomena called biomagnification, where a small fish may have a certain amount of a pollutant in them, but a larger fish, a predator, which eats small fish, will have a much larger amount and concentration and proportion of that pollutant in them. I could give you lots of examples. Birds, hawk DDT, and rodents dying, eating stuff which has DDT in it, hawks or eagles preying on the rodents, and the levels of DDT in the hawks were such that it affected their fecundity. Their eggshells were very thin, and that led to the phasing out of DDT in many parts of the world. Anyway, how do we know what is bioavailable and available to what? We're going to look at an old lead, tin, silver mine in Cornwall called Wilbetsey. Okay, so this is Wilbetsey. It's on Dartmoor in the United Kingdom. There's a whole series of these mines. This is the old pump house, cable house. So the mine shafts were under here and under here. There's a whole series of these. They're on the metalliferous aureole. The whole of Dartmoor is a granite intrusion, and effectively you get local hot water circulations as that's intruding, and that deposits lots of very valuable minerals. So this particular mine was used for lead, copper, tin, silver, and the mineralogy is quite pretty. Also contains arsenic, antimony, sulfur, zinc, and iron, and there are various ores here. Okay, these hills here are literally spoil heaps where they put the minerals they didn't want. Typically arsenites, antimony, various things that at that time didn't have any value. And they just left them there. So, is this area a total death trap? Is it loaded with heavy metals, with lead, copper, tin? The mine closed 150 years ago, so not much technology then. A lot of what nowadays will be considered quite rich ores were just dumped here in these tailing pits, heaps. Because for this to be a death trap, those metals must be bioavailable. To cut a long story short, they're not bioavailable. You can find these minerals in the streams, in the stream beds. No, the minerals are stable. It's not bioavailable. Therefore, it's not a death trap. Things live quite happily in this area. Bioavailability, really, really important to know what is bioavailable, to what, and what isn't. Okay, so I said we weren't going to spend time in ecotoxicology. I'm really more interested in bioavailability, so I'm not going to read this, but if you're really interested in this sort of area, you've got to understand that bioavailability is different at different times. Different stages in an organism's lifestyle. It could be really dangerous for them, at other times not. Okay, I think we should move on. Summary of what we've talked about so far, and underlining that a lot of the chemistry that transforms pollutants is biological chemistry. It's the biology that does a lot of this. Now I'd like to show you a real example. Glyphosate is a very widely used weed killer. The problem with it is not so much about the glyphosate itself, but what it is oxidized to in the soils. So this is glyphosate, and it's a great weed killer. It hangs around a bit in the soil, and it gets biologically transformed into AMPA. AMPA is more than an order of magnitude more persistent than the original glyphosate. So that means that when you've got leaching of this stuff, because both of these are reasonably polar molecules, into water bodies or aquifers, then actually it leaches for much longer than it would otherwise do. Okay, so the degradation is first order. To give you a feeling of scale, about 1.5 million tonnes of glyphosate is made every year and sold. And the half-life of the glyphosate depends on what sort of soil you're actually doing the reaction in. Typically in clays and clay topsoils, it persists for longer than in sandy soils, because in sandy soils you get lots of water percolating through and it's dissolved and taken out that way. This is the kinetics, and again we've got the clay soils up here, the sandy soils down here, showing you the persistence of the glyphosate and its reaction products in the soil. The impact of pollutants is, as we already alluded, determined by their partitioning, their speciation. We've talked about Henry's law already, so I'm not going to talk about that anymore, but I'm going to look at a couple of examples. Mercury, inorganic mercury. Life has a habit of trying, or certainly in plants actually and mammals, seem to need mercury about as much as they need a hole in the head, and they look for ways to get rid of it. Now, plants methylate mercury, methyl mercury or dimethyl mercury. It's very volatile and actually more bioavailable. So if you're looking for an initial mercury spill, an inorganic mercury spill, and you've left it a little while, you're going to be looking in the wrong place. It won't be as mercury metal anymore. It will be in the river or the soil water or the atmosphere as methyl mercury. The references here are where the data's come from, and you can see the speciation of the various compounds, or rather their Henry's law constant. Another example, diazinon, very widely used, widely banned, insect neurotoxin. It's soluble and persistent in water. Now, how is it bioavailable? It's a pesticide, so what you'd hope is the pests would ingest it or come in contact with it, and then it would do their job, or rather do the job it was designed for. In soils, it's relatively it tends to sit in the soils for quite a long time, and its main route of availability isn't via water. You actually it has a partial pressure which is not insignificant. So in the soil void, in the air voids in soils, you have a partial pressure of diazinon, which is the thing that is absorbed by the targets and ends up killing them. However, when it gets into the water, it stays there a long time. It's very widely available to the insect and fish ecosystems in water, and it causes a lot of problems. So, the chemical properties of a substance determine its impacts. I probably won't talk about this because I've already talked about it. KD, the partition coefficient, and KOC, the octanol water partition coefficient. And this is the amount of organic matter. So I'll just move on and look at other reaction sites, I suppose, or reservoirs, reaction venues in waters. And actually, solid reaction surfaces in waters, colloids. So you've got three colloid types: hydrophilic, hydrophobic, and association colloids. I'll briefly look at all three of them. For hydrophobic and association colloids, they can be broken, the colloids can be broken by adding salt. But let's first think of what a colloid is. It's a suspension of tiny particles in water such that the water appears clear. It doesn't get cloudy. There are some very nice experiments to identify whether colloids are present, which I'll leave you to discover. But the particles are small enough that they don't aggregate. They stay in solution or in suspension. Okay, so this is an example of a polar, a hydrophilic colloid, for instance proteins, where you have charge on the particles balanced by charge in the water, and this is what keeps them separate, because there's no attraction for one colloid particle for another. Okay, association colloids. Typically a detergent is polar one end, not at the other, and you maybe have a polar substance or just a coordinating substance in the middle. Certainly it's a water-insoluble substance, but you get this whole range of effectively micelles, the non-polar end linked to the particle, and the outer part is polar, so the whole particle becomes a colloid. So water-insoluble organic matter miraculously can be dissolved. Okay, other types of colloids or particles. Metal oxides, if this is a metal oxide surface, it can be hydrated, and then it can either gain hydrogens or lose hydrogens. Whatever, it means that the surface of metal oxide particles in water are usually charged. I won't bore you with the 0-point charge that you have dealt with in your earlier years, but effectively changing the pH changes the 0-point charge and allows not only charged reaction surfaces in waters, but also allows you a degree of ion exchange with the surface ions. Normally in fresh water, most of your colloids are negatively charged. So typically this will be what's coming down a river, negatively charged colloidal particles. Estuaries are the great particle reactors. You get a meeting of these negative colloids with sea salt, high ionic strength of ions. Effectively you get supercolloids formed, or superparticles formed, which then break apart. So the water coming into an estuary, the colloidal particles are normally negatively charged, leaving the estuary they're positively charged. The estuary is the place where most of what comes down a river, like the heavy metals and stuff like that, is dumped. One day soon, somebody will start mining estuaries. They're very rich in organics, pesticides, metals, because they are the natural protective system of the oceans from our pollution, which usually goes into rivers. Okay, last few slides, still on colloids. So humic substances are very good at tying up aromatic species, often using oxidoreductase enzymes, which are in the waters made by biological organisms. So again, when this happens, you form colloids, and eventually this material is dumped in the estuary. quite glad those sort of processes occur, really. Certainly protects the oceans. That means that sediments are significant sinks for metals. There's large carbon and sulfur inputs, and these sediments usually, because of microbiological processes, actually display significant redox potentials. We won't look at them in this module, but in something like environmental chemistry, for instance, we'd look at Pourbaix diagrams to model what species you might expect. And here's a small table to show you the types of metals and their form in oxidizing conditions, which will be in the water column, and their form in the sediments in reducing conditions. Sediments also not only are the final resting place for many, many particulates, they also re-release some of these substances, metals, back into the ocean or in the lake, the bottom waters of lakes. Because very often the fact the sediments are anoxic means that other chemistry can happen, which then gets to release again into the water. Other particulates, a series of clays. They're very good ion exchange properties. They have charged surfaces because of the hydroxide or H+. Often used in natural water cleanup of natural water systems, but clays are a major biogeochemical interface. And I won't talk about it more here, but do read in Manahan about those. Surface absorption, typically defects in metal, surface particulates. So you have metal absorbing on those active sites or those defect surfaces, which then allows complexation of some pollutant actually on the particulate. Equally, phosphates, sulfates, and various other similar electrostatic interactions. So particles are interesting because if the particle then drops out to the sediments, everything on the particle also drops out to the sediments. Okay, so in terms of these physical systems and biological systems, many effects flow from these biological processes mediated by the chemistry that we're actually not too unfamiliar with. Things like bioaccumulation, biomagnification, and how this has health effects for humans and animals, but also how it distorts ecosystems and change, which is population statistics and ecologics. They're called unintended outcomes, but we're not going to spend any time on them here. Final slide, prevention. I'm not going to talk about it now, but there's a whole tranche of planning acts and regulations to control what is built, where and when, what is emitted, along with things like the Environment Act and the various water acts to control what is polluted, what you can emit, what the pollutants could become. Not green chemistry, but you can see the link, I'm sure. Any substances that does get used in the environment needs a resource consent or regulatory approval from various bodies depending on where you are in the world. And of course, these environmental standards are enforced by various authorities. Okay, I think we're done. Thank you very much for listening, and see you soon. Take care.